Welcoming to the stage now, another great speaker from a company called QDrant. I'm sure many of you know it, the vector database company, open source. So Kacper, you're from Poland, right?
Yeah, I came from Poland just this night.
All the way. Thank you for coming. So QDrant, I'm sure you're going to tell us more about hallucinations today and how to reduce them.
Yeah, sort of. Actually, I'm not really sure if I have a cure for hallucinations, but definitely I was speaking about some methods of how to mitigate them and how to bring our own data into LLMs.
Awesome.
That's something that is actually a blocker for many companies, I guess.
Yeah.
At least for our users.
Yeah. By the way, Lily, the little girl that joined us on stage this morning, she was telling me that if AI becomes too perfect, it will be inhuman. So what do you think about that?
Well, I don't feel like we are currently in a situation like AI becoming really as good. Maybe in some specific tasks, but overall, I will also try to ensure you that it's just a stupid machine that does very little thing, but with lots of parameters that are being learned. So it's really we are shooting with an.
Yeah. So interesting discussion. Hallucination. Yeah, I think we as humans, all of us hallucinate, maybe sometimes on stage as well. So I think it's part of being human, right? So kudos to OpenAI and all the companies. We don't judge you for hallucinating. It's what makes us human and what will make AGI closer to human nature.
It's
good.
Are we done? Great. Thanks a lot. Unfortunately, some issues with my Linux machine. Although I recommend using Linux for the development, it's probably not the best OS to present. But unfortunately, that's my preferred choice. As already mentioned, I'll be speaking today about hallucinations, but also some ways of how to reduce the impact of hallucinations on your business if you are happy enough to start incorporating LLMs into your existing projects, and also how vector databases might be a key component in that landscape. As already mentioned, I'm Kacper. I've come from Poland, and I work for QDrant. And we are building an open source vector database. However, I hate this term. For me, it's more like a vector search engine, but industry already adopted this name, so unfortunately, we need to follow the trend. This is not like a database, and the expectations for a real database are a bit different, although, well, it is as it is, and we cannot change it right now, so unfortunately, we need to call ourselves that way. And before we start speaking about the technical details, I would like to start with a brief lesson of history. Since QDrant is a German-based company, Germany-based company, I asked the following question to the ChatGPT. What was the capital of Germany before Berlin? I know from my history lessons that there used to be a different capital, but I just didn't remember the proper name. And the answer was pretty plausible. That was Frankfurt am Main, which is an existing city, so why should I suspect that something is wrong with the answer? And unfortunately, after a quick Google search, it turns out that Bonn, a different city, used to be the capital before Berlin. Actually, we need some more context to answer that question, and that wasn't that obvious for ChatGPT this time. Because Germany used to be divided into west and east part, and one of them, west part, has a different capital before Berlin. East part existed for like a few dozen years, so unfortunately, well, it didn't have a previous capital. So ChatGPT definitely lacks this historical context to answer my question properly. But does it make it any useful for building reliable projects if it cannot handle this kind of simple questions? Well, apparently it does, but that requires to build some additional guardrails around it. And today I would really try to describe the pipeline that you could try to build with some existing open source tools to mitigate that risk. And this phenomena of making up an answer is called hallucination. And hallucination is a confident response of an AI system that cannot be justified by its input data. And input data is both the training data that in case of ChatGPT we have no access to actually, and also the prompt that we send, because obviously we could also put some more information, and that's also the input of the whole system. And there is still an ongoing discussion about if hallucination is a proper term to describe this, this behavior. Actually, some people claim that we should find a different term because hallucinating in, like, person who would be hallucinating wouldn't be making up this, false statement. That's a different phenomena. Like, I like it. It's also hard to say if that term is, if that definition is correct, because we do not have access to the training data. Actually, ChatGPT was trained on huge data sets. We love to say that it was trained on the whole internet, but we don't know what exactly was put inside. Maybe there was like a false statement that Frankfurt am Main was just a previous capital of Germany. I don't know. And I'm not gonna discuss that much, like how we should call different behaviors. I would love to speak about why the hallucination happens, and it seems that it traces back to the training process of the LLMs. If you don't know it yet, I encourage you to have a look at the State of GPT presentation by Andrej Karpathy. I put a link at the bottom of this slide, and actually this slide is taken from his presentation, and that describes various stages of fine-tuning or training the large language models. And everything starts from the pre-training phase, and in the pre-training phase we have lots of data, but this data is of a really low quality. It is just web scraped and saved somehow, so it can be read by the training process. And as you may see, the algorithm used in that training, the objective of the training was to predict the next token. So it's actually a more sophisticated autocomplete. Like in your mobile, if you write a lot of text messages, at some point it starts to remember what are the words that you should put in a sequence. And that's basically the whole goal of that. So it takes part of the text and try to predict the next word, actually a subword-like unit. But it has so many parameters, like billions of parameters, that it is actually able to remember even complex context and make some answers that sounds really, really plausible. And this is, that gives us a base model that we can already deploy, which is, well, this kind of models are not that useful. They're just used as some sort of autocomplete, but they are used as a base for supervised fine-tuning or reinforcement learning with human feedback. So after those stages, we can expect to have a better model that works more like an assistant. So we give them a task, it still produces a sequence of tokens. As you can see, the language modeling here in the supervised fine-tuning also focuses on predicting the next token in the sequence, because that's in a nutshell how these models work. But this time it does not predict the sequence only, but it also considers what was the goal what was the prompt, what was the overall goal of that I gave the model to. And here, the training is not based on low-quality data anymore, but we have pairs of questions and answers, or tasks and answers written by contractors. So this time we have data with way higher quality and lower quantity. And the same applies for reinforcement learning. Here the data is also of higher quality, but the process is just a bit different. And depending on the model, it may just undergo only the pre-training phase, maybe pre-training and supervised fine-tuning, and in the best case, all those phases. But overall, the whole goal of these systems is to predict the next token in a sequence. just the objective function or the way we measure how well the task was solved is different. And just to give you like an intuition of what is the difference between the base model and the fine-tuned model, here is a screenshot of two models, DaVinci and Text DaVinci. So basically, with the base model, if you just put a specific task, it will probably start to generate some similar sentences. This is just a sequence of questions that could be asked, assuming that my prompt was just one of these questions. And in the fine-tuned model, we can already expect a valid answer. So they are more suitable for chatbot-like experience and building reliable applications, because they actually solve the problem, not generate a specific response. By the way, base models might be also cheated to work as assistants, because we can just write some sort of dialogue, user and assistant's answer, and provide a few examples, and then it will just continue the conversation, because it predicts the next token. GPT models are just trained to solve this very easy tasks, like predicting a single word, let's say, or a single token, given the context. But because they have billions of parameters, they can capture way longer relationships than the old methods that we use. For example, the same applies for naive bias and n-gram-like modeling, but then we were just modeling based on a very short context window. Now we have thousands of tokens possible to be incorporated, and because the transformer architecture incorporates this attention mechanism, it is also well suited for text-like challenges. And if we think about how the predictions are created with large language models, there are actually two components of that prediction. And the first one is those parameters that our network learned during the training phase. I don't have like a correct term for that. I don't want to call it knowledge, because apparently it's not knowledge. It's just a set of numbers, set of weights, which are just multiplied with our input data or some intermediate numbers created by the system. So there are some sort of rules, but it's definitely not like an artificial brain. We try to imitate the behavior of humans' brains, but apparently it hasn't started yet. We are just using very simple means, very simple mathematical operations to achieve that. And because of the complexity, we are able to grasp a lot of context. And this is the first prediction component. So if I just ask this original question, what was the previous capital, the answer was solely based on the learned parameters. But there is also another component, which is the context and literally everything that we put into the prompt. In my example, the prompt was just the task that I wanted to solve with LLM. And obviously, it didn't contain any hints that the model could rely on, so it just failed in that case. And if we think about how can we mitigate the hallucinations or how we can reduce the impact on our systems, the first idea that can come to my mind, to your mind, would be, let's just fine-tune the model. We have our own data. We know like that our users are going to ask very similar questions, or their questions will be just based on our internal knowledge. Let's just fine-tune the model, and then it should be able to handle all the cases of our users properly, or at least majority of them. That's incorrect, unfortunately. Of course, you can incorporate some new facts into the system, but continuous training of large language models is actually impossible. They are being trained for weeks, months, and even if you would like to fine-tune them, there are no guarantees that they will gather all the possible cases and they will learn how to solve the problems that your users may have. So there are no guarantees here, and the problem itself, the process itself is very expensive. If you have a look at OpenAI pricing, it starts from $2 million, as far as I remember. just to put some new information into the model. But LLM is actually just a neural network with a set of parameters. And there is a certain number of parameters in each model, so it has some sort of capacity. So we never know if you perform the fine-tuning process, you never know if it forgot some of the past ideas or if it just expanded it. But there is a capacity, so it cannot handle anything beyond that capacity. So it's a bit different comparing to human brains, because obviously the structure here is just more complex, and also the neurons that we use in neural networks are different. But there is a certain limitation, and it's hard to control whether our LLM already know everything we wanted it to know, because we would need to set up the data set with all the examples that you expect to have. And actually, LLMs are just stupid machines generating the next token in a sequence, but with lots of parameters, they can do it pretty well. But there is no reasoning inside, so AGI, artificial general intelligence, is still far away, and definitely we won't be able to achieve that with the means we currently use to implement it. Still, that doesn't mean that they are useless, because they may already be adopted into many domains, and many industries may just benefit from using them. So there is an alternative approach, because we have two prediction components. We have those rules or knowledge that model was trained for using the training data, and fine-tuning is expensive, so we can control the other one. We can make sure that we incorporate some useful information into the prompt directly. So model can rely on its language capabilities instead of knowledge that it learns in the training phase. So we are actually converted knowledge-oriented tasks into language-oriented ones, which should be a bit different, because in the supervised fine-tuning, these models are usually given some task like rephrase given text, or summarize it, or extract some useful information. So those are just some sort of language capabilities, but not knowledge-oriented questions. So, coming back to the original example, if I just put the first paragraph of Wikipedia about Berlin, there is already an answer to my question. So instead of asking the question directly, I'm just rephrasing that and putting this additional context so my model can rely on it finally. And this time, the answer is, first of all, very short. So it's even better for my case, because I just asked for a specific name of the specific city, not like the history of it. And the answer is accurate, and it's based on the text that I provided. By the way, this example was created using GPT 3.5, and it doesn't work in GPT-4 anymore, and it doesn't make things any better, because with GPT 3.5, we knew that there are some sort of hallucination problems. With GPT-4, it just became a bit tricky to find these examples, but it doesn't mean they do not exist. They are just hidden because OpenAI just fine-tuned the model on our past interactions. We just let them use our interactions to make the models even better. So that doesn't mean that hallucination won't happen with GPT-4. It's just a more complex structure, so it might be just not that often. And there is a problem of how we can incorporate this additional data into the prompt. Obviously, I won't be using a Google search in another tab on my browser. I won't be putting the paragraphs from Wikipedia to enrich my prompt. I want to have a scalable solution that would automatically detect what is relevant and put it into the context so I can automate and streamline the process. And the solution for that is Retrieval Augmented Generation, RAG, which is currently built by a lot of companies, because that seems to be the only reliable way of how to put our private data into the LLMs without fine-tuning them continuously for millions of dollars. And apparently, Retrieval Augmented Generation is just a pretty fancy name for a fairly simple problem, because retrieval component in that RAG pipeline is just some sort of search engine that finds relevant items in our knowledge base and put them automatically into the prompt. And that might be solved in different ways, but we've been trying to solve the problem of search for ages. So it's nothing new. But the name is, of course, pretty cool. We have a cool problem and a lot of frameworks around it. Think about LangChain, Llama Index, HiStack, a lot of tools that try to find solution for that. But search problem is nothing new. We try to solve it for ages. And there are various ways of how to perform search operations, if you think about it. The most naive one would be to use keyword-based search. So we have a query, and based on the query, we are just trying to find documents with overlapping terms. So that's fairly easy. Of course, there are some additional methods of how to convert words into the root forms, but overall, the idea is pretty straightforward, and there are lots of tools to implement that. But apparently, with large language models, we want to have this natural language-like interactions. So we don't want to use the same terminology that was used in our knowledge base. Let's say you work in medicine, and all your facts, all your data in your knowledge base was created by the domain experts, like doctors or some other medical professionals. They know a specific terminology, which is not that commonly known for your users, maybe just your patients. And maybe some of your patients are just home-trained doctors. But overall, they won't have this knowledge. They will miss a lot of facts and a lot of words which are commonly used by professionals. That means there is a vocabulary mismatch, because your data and your users speak different languages. And that's why vector search, semantic vector search, seems to be a solution for that problem. Semantic search is based on neural encoders or embedding models. We call that differently. But basically, those are just some sort of deep neural networks which are able to take unstructured data and convert it into fixed dimensional vectors. So the size of this embedding vectors is just like hyperparameter of the model itself. And there are plenty of models available out there. There are some open source ones, but OpenAI or Cohere or Aleph Alpha are also SaaS providers of this kind of solutions. And the main property of that models is that if the input object, if two input objects have similar meaning, their vector representation should be close in that vector space. And if you just compare every single dimension of these vectors here, you can see that the numbers are almost identical. And that means if we calculate the distance between those two vectors, it should be relatively small. And that's the whole idea. We use cosine distance to calculate, like, there are various ways, but 90% of the cases we use cosine distance, and it's also based on the model you selected. And if you would like to find some open source tools for that, there are sentence transformers library, there are FLAC embeddings, Fast Embed, which is like a side project of QDrant as well, and they all expose this kind of models. They are also pretty lightweight comparing to LLMs, because embeddings might be calculated easily on your CPU. Unfortunately, that doesn't work that well with LLMs. But that's the whole idea. In our case, different terminology was converted into similar representation. And semantic search might be it's thought to support synonyms out of the box because it was trained on huge corpora of data, and it just derived the meaning of words based on the context in which they often appear in. So two different words having a similar meaning should have similar vector representations, and they also can support multiple languages at the same time. So if you have documents in English, you can use Arabic to find the relevant ones without translating them in the meantime. Of course, assuming your model supports both of these languages at the same time. And there are vector databases, tools that are commonly used to implement that, because vector search has one small challenge. The process looks as following. We have a bunch of documents that we vectorize, and then we want to find the relevant ones based on the query. But if you have millions of documents, that means that for every single query, you would need to calculate millions of distances and select the lowest ones, because these distances cannot be pre-calculated, query is unknown. And that's what vector databases are primarily designed for. They provide this vector search capabilities, but this is some sort of approximation, so we don't need to calculate the distances to all the points in our data set. So the original idea was to send the prompt directly to the large language model and expect the answer. But after the enhancement made by retrieval augmented generation, there are two additional components. We use this prompt as some sort of query that gets vectorized by the embedding model, and then our knowledge base, which is usually a vector database, selects the most relevant documents, the most relevant pieces, and incorporate them into the prompt. So we do not send the original prompt directly, but build some sort of meta prompt with all these relevant documents incorporated into. And in practice, that means that we have two separate processes, and the first one, the indexing process, is a bit challenging. It may just look simple, but this is pretty a bottleneck of all the systems, because we have a bunch of documents. And documents might be, I don't know, like FAQ from your website, maybe some customer cases, some interactions you had, maybe some huge PDF documents, some sort of documentation, even your source code if you write software. And they cannot be directly converted into vectors. Let's imagine a PDF, like a book, which is stored as a PDF document with, I don't know, 500 pages. It's hard to describe a whole book in a single sentence, so we cannot expect a single embedding to get all the meanings of a whole book. Instead, we need to divide our documents into chunks, and this is a real challenge in that, how to do that properly, because those chunks should be small enough to capture a single idea, but also long enough to be meaningful. So this is a challenge itself. There are various strategies. The most naive one is just to use a fixed window size. So we use, I don't know, 300 words. We do some overlap between the chunks, and that's it. But there are also some other more advanced approaches of let's use embeddings and find like group together sentences which have similar meaning and do some cutoff once we change the topic. But overall, it is a challenge itself. But also, if you have millions, but we also have setups with billions of documents, you need to pass all the documents through your neural encoder, which is a bottleneck of the whole indexing process. Those neural encoders are lightweight comparing to LLMs, but still they require computing power. And if you want to do that, you probably just use some sort of cloud provider, just not to buy lots of GPUs, just for one-time indexing process. But of course, you may have some updates, so this is not that straightforward as it may look like. After all, after we process all the documents through the neural encoder, we have the embeddings that we store in the vector database. A good practice here is also to use these input documents and store them in the vector database as well, along with the vectors. QDrant and majority of vector databases out there have some support for metadata. In our case, it's called payload. So instead of having just high-dimensional vectors, we also have the input data that was used to create them. That makes a lot of sense. If we want to build retrieval augmented generation, we need that content to put into the prompt, so there is no need to call another system in that setup. And the next process is pretty straightforward. We have a query, our prompt, that we pass through the same neural encoder. This is called B-encoder architecture because we use the same encoder twice. Sorry. We have a query embedding that we send to the vector DB, and by calculating the similarity, it produces a bunch of candidates. So those are the most relevant documents for a given query. That's as simple as that. But apparently, retrieval augmented generation is a great tool to make LLMs more resistant to hallucinations, because we no longer rely on their internal knowledge. But there are many other things that you need to consider if you really want to implement that. And prompt engineering was one of the hottest topics of the previous year. It's still very important. Also, tweaking this retrieval process, because the one that I described is just a very simple, happy path. But of course, there are some additional tweaks that you need to perform. and that might be controlled. You may choose a different model, so testing it is not that easy. But overall, except for the retrieval, if you are sure that your retrieval works well, there is also some additional work that has to be done. For example, prompt engineering in that case. This is the problem that we all know, especially those who have implemented something with LLMs already. They tend to make us happy. They just want to solve our tasks that we gave them, no matter if the answer is correct. I just asked for 5 countries with names starting with letter R. One hint here, there are just 3 countries like this around the globe, so it's not that easy. The model should know that. But basically, it's just making up the answer. The 4th one, the Republic of the Congo. Actually, there are so many republics around the globe. I don't want to have all the republics. That doesn't make sense. I come from Poland, which is officially Republic of Poland. That doesn't make the difference. But the 5th one is already the most stupid that I could imagine, Qatar, which doesn't even start with the expected letter. But model just wanted to make me happy. I wanted 5 countries, so it gave me 5 countries. By the way, those 3 first ones are the only possible ones. So my solution for that was to let the model to produce a shorter list if there are not enough countries. And do not make up any answer if they are incorrect. What already gave me this answer, so Qatar is not there anymore, but apparently I have lots of republics, so I just need to be more explicit here, and I need to let the model omit the countries that could possibly start with republic, and that already gives me a final list which is correct. But this is just a trial and error approach. Probably it won't scale, it won't be like universal if you use a different model. By the way, if you are an expert with prompt engineering for ChatGPT, that doesn't transfer directly to different models. I've recently played with Phi-3, which is a small language model that I could easily run on my CPU. And this is pretty good. Like, if you would like to create misinformation and fake news, this is already a great tool by itself. But apparently it seems that it works pretty well with retrieval augmented generation. I guess that was just how it was trained. So really encourage you to have a look. Definitely way better if you can achieve your task with simpler means that can be launched on very like lower end machine. That should be even better because you can easily reproduce and scale it up. And prompt engineering requires a lot of work. There are already some existing tools for that, so you can version the prompts you have, which is pretty useful if you use, for example, LangChain. You might be a victim of the default prompt. The defaults of LangChain are pretty okay. They used to be a bit worse in the past. I know lots of companies complaining that their retrieval augmented generation just started making up some answers about Michael Jackson. Apparently, Michael Jackson was part of the default prompt of LangChain, and that was the only reason. It was just mentioned, so if the model was struggling to find the relevant content in the context provided, it was just using some of the random names used in this default prompt. So you might be a victim of the default prompt. It's better to know what you send to the LLM. And the first idea to test if you struggle with the quality of the results is to allow the model to not provide the answer. They were just trained to fulfill our request, so they are forced to always generate a response even though they don't know it. So if we allow them to just declare that I don't know the answer was not provided in the context, that already gives us a bit better quality. Of course, some people try to ask the model to provide step-by-step reasoning scheme, which is okay if there is like a human feedback in the loop. So if there is someone reading this reasoning scheme and seeing whether there are some gaps in it. But even if you ask for a reasoning scheme, that doesn't mean that the model performs it. It still produces a sequence of next tokens. That's it. So there is no reasoning inside, unfortunately. Also, if you implement that retrieval augmented generation, you can also put some identifiers next to your documents, probably provide a format that will be easy to follow by the model, and some of them already support JSON quite well. So probably that makes a lot of sense to put the context as some sort of JSON document, and then you can ask the model to provide the sources it used, so the document ID it used to generate a particular response. But there are many, many additional strategies here, like step-back prompting is one of them that I like most probably, because that applies well for more complex domains. So for example, if you would ask a question about quantum physics, a step-back prompting will, first of all, ask the LLM to ask a more generic question. So probably it will generate a question, what is quantum physics, or what are the basics of quantum physics? And then you will have like 2 separate prompts, and both might be used to extract relevant documents. So the original one would provide you, hopefully, provide you with some documents that are relevant to answer that particular question, and the more general one will provide you with some general ideas behind quantum physics in that case. But there are many, many more, and many people try to incorporate some new strategies for that. And one scheme that I feel is quite undervalued in the whole world of the LLMs is semantic caching, which is quite useful if you already have retrieval augmented generation in place. Because obviously, in the most naive approach, you would just send your prompt directly to the LLM or extract these relevant documents and then send it to LLM. But probably your users will have a tendency to ask similar questions, to have similar problems. So definitely, the solutions might be also similar to each other. And since we already have this embedding model in place, and we can calculate the similarity of the current query to the past queries we had, it's quite easy to implement some sort of cache. So let's say I have a query, I try to find some similar queries in the past, and if I successfully extract something which is similar with the similarity score higher than 0.9, let's say, this is pretty tricky to find a good threshold here, I can already provide an answer that the LLM produced in the past. This is also pretty useful if you would like to detect misuse of the system because someone just wants to perform like an adversarial attack on the prompt you send and try to force the model behind to produce the content that it should never produce. In that case, if you detect that a specific query is just too far from all the past queries because the highest similarity for it is just definitely lower than expected, then there might be like a human intervention in the loop just to make sure that somebody cannot use our tokens that we pay for to generate some content we would never want it to produce. So various applications of semantic search. By the way, it's also a pretty universal method for classification, regression, anomaly detection, recommendation systems, and so on. But there is still plenty of things to do, and retrieval augmented generation is just a very basic pipeline that may help you to reduce the risk of hallucinations in your real-world applications. If there are any questions, I'm happy to answer them, but if you would like to stay in touch, this QR code points to my LinkedIn account, so please feel free to drop me a message. And that was a real pleasure to be here. Really enjoy being in Jordan. Thanks a lot for the invitation.